Welcome back to our series of current electricity. This is lesson 6, A-level physics, prepared by Joseph Mayanja. In our previous lesson, we discussed the factors that affect resistance of the conductor, and among those factors, temperature was a pivotal factor. Then we also talked about the length of the conductor and then the cross-sectional area of the conductor, and those three factors were very paramount when it comes to the resistance of the conductor. In today's class, we want to discuss the temperature coefficient of resistance, and it is noted by that symbol, this letter, and this letter is alpha. We define the temperature coefficient of resistance of the material as the fractional change in the resistance at 0 degrees Celsius per degree Celsius rise in temperature. What that means is that when you increase the temperature of a conductor, or when you increase the temperature of the material, what happens to the change in resistance? For some materials, the temperature coefficient of resistance is negative, and for some materials, it is positive. If the temperature coefficient of resistance of a material is positive, it means that for a change in temperature, the increase or the change in resistance is positive. And when the temperature coefficient of resistance of the material is negative, it means that for any increase or for an increase in temperature, the change in resistance is negative. So if a material has a resistance R0 at 0 degrees Celsius, and its resistance increases to R theta when heated through a temperature theta, then we have this relationship that relates the temperature coefficient of resistance and the change in temperature. And alpha here is the temperature coefficient being equal to R theta minus R0, this standing for the change in temperature. And then R0 is the resistance of the material at 0 degrees Celsius. And then R theta is the change in temperature. It can be from 0 degrees Celsius to 20 degrees Celsius, or it can be from 30 degrees Celsius to 40 degrees Celsius. Then the SI unit of temperature coefficient of resistance is per Kelvin or per degree Celsius, simply because the numerator here, since this is resistance, change in resistance, then it is in ohms, then the temperature here can be in Kelvin or degrees Celsius, then R0 is in ohms. So when you divide this and this, what you have is 1 over K, or you can have 1 over C. Then this becomes per degree Celsius or per Kelvin. The above equation can be rearranged into R theta is equal to R0 into 1 plus alpha theta. And a graph of R theta against theta is a straight line whose intercept is on the R theta axis is equal to R0, which is the resistance at 0 degrees Celsius, and the slope is alpha naught. From the above expression, which is alpha is equal to R theta minus R0 divided by theta R0, when you cross multiply, you will have alpha theta R0 being equal to R theta minus R0. When you make R theta the subject, R theta becomes R0 plus alpha theta R0. You factorize out R0, this becomes 1 plus alpha theta. So this equation has been simplified, and in case you encounter a question, you can just apply this equation and then be able to solve any problem. A graph of r theta against theta looks like this, and we are saying it is a straight line, and in the intercept on the r theta axis, this point here, is r naught, which is the resistance at 0 degrees Celsius, and then we can calculate the slope from this expression. The change in r theta, the change in theta, gives you the product of r naught and the temperature coefficient of resistance. Remember the relationship that relates temperature coefficient of resistance alpha is equal to r theta, which is the resistance of the material at a certain temperature theta, minus r naught, which is the resistance of the material at 0 degrees Celsius, divided by r, then times 1 over change in alpha. This can be rearranged as change in resistance, which is r theta minus r naught, divided by change in temperature. And we are saying this is the same as alpha. So alpha being equal to the change in r theta minus the change in temperature times the resistance at 0 degrees Celsius, multiplied through by r naught, multiplied through by r naught, r naught. This expression here is this one, and therefore this expression is what we have here, and that is the slope. Therefore, that is why we are concluding that the slope S is equal to temperature coefficient of resistance times the resistance at 0 degrees Celsius, which is r naught, and therefore we get this expression. And in this expression, we are saying from the graph, if you want to calculate the temperature coefficient of resistance, all you have, calculate the slope, divide by the resistance at 0 degrees Celsius, and then that will be the temperature coefficient of resistance of that material. For a case when you have R1 and R2 as the resistances of a conductor at temperature theta 1 and theta 2, then you can come up with a relationship that can help you solve such a problem. From this equation, r theta is equal to r naught into 1 plus temperature coefficient of resistance times the temperature. R1 will be equal to r naught into 1 plus alpha theta 1. Let us call this equation 1. Then R2 will be r naught into 1 plus alpha theta 2. This is equation 2. Now, when we divide the two equations, dividing equation 1 equation 2, we come up with R1 divided by R2 being equal to 1 plus alpha theta 1 divided by 1 plus alpha theta 2. And this relationship can help you solve a problem where they have given you different resistances at different temperatures of the conductor. This can help you calculate the temperature coefficient of resistance of that material. For some materials, they have positive temperature coefficient of resistance and negative temperature coefficient of resistance. Specifically for metals, they have positive temperature coefficient of resistance, and we want to understand why. When the temperature of the metal increases, the amplitude of vibration of its atoms also increases. This reduces the mean free path of the conduction electrons, because as the atoms vibrate, they block the passage of these conduction electrons, and therefore reducing the mean free path. Thus, fewer electrons now flow per second through the metal, and hence this increases the resistance of the material. For example, if at 0 degrees Celsius the resistance of the material is, for example, 20 ohms, and then when you increase the temperature to, for example, 10 degrees Celsius, that is of a metal, the resistance at that temperature is 100 degrees Celsius, because we have said that when you increase the temperature, this increases the resistance. Now we know that temperature coefficient of resistance is change in temperature, which is R theta minus R naught, divided by the change in temperature times the resistance at 0 degrees Celsius. Therefore R theta in that case is 100 minus 20 divided by the change in temperature is also 20 times the initial resistance, which is also 20. In this case, the numerator is positive, which is 80 divided by 400. This is positive. That is why we are saying that for metals they have a positive temperature coefficient of resistance, simply because an increase in temperature increases resistance. Therefore, the fractional change in resistance will be positive for any change in temperature. Now for semiconductors, they have a negative temperature coefficient of resistance, and we want to understand why they have a negative temperature coefficient of resistance. We know that semiconductors have fewer electrons available for conduction at room temperature. So when the current is passed through it, the material heats up. As the temperature increases, loosely bound electrons are released for conduction, thus the current increases. Hence the resistance instead reduces. We know that conductivity is just the reciprocal of resistivity. But for semiconductors, as the temperature increases, it results in an increase in charge concentration, meaning that the increasing conductivity causes the resistivity of the semiconductor material to decrease, because the two are inversely proportional. As the conductivity increases, the resistivity has to decrease. This happens with a rise in temperature, and this automatically results into a decrease or a reduction in resistance of the material, and therefore it means that the fractional change in resistance per degree rise in temperature becomes negative. For example, if at 0 degrees Celsius the resistance of that material is 10 ohms, and at 20 degrees Celsius the resistance of that material is 5 ohms, it means that the temperature coefficient of resistance, which is the fractional change in resistance, will be negative. Why? When you do the substitution, we know that alpha is equal to R theta minus R naught divided by the change in temperature times the resistance at this 0 degrees Celsius. R theta is 5, R naught is 10, the change in temperature is 20 times the initial resistance, which is 10. This becomes negative 5 divided by 200. And this implies that the temperature coefficient of resistance is negative. And we have said that when the current is passed through, this simply means that the conductivity has increased, and when the conductivity increases, the resistivity has to drop, and resistivity is directly proportional to resistance. As resistivity decreases, it means that even the resistance reduces, and therefore the fractional change in resistance per degree rise in temperature has to be negative. However, superconductors are materials whose resistance vanishes when cooled to about negative 273 degrees Celsius. This is what we call the absolute zero temperature, and that at that temperature all materials are said to have negligible volume. Therefore, we are saying for the superconductors, their resistance at this temperature vanishes. Let us see how we can solve this problem. In this problem, we have a coil of wire and has a resistance of 30 at 20 degrees Celsius, the resistance of this wire is 30 ohms, and when the temperature is 60 degrees Celsius, the resistance of this wire is 34.5 ohms. We are required to calculate the temperature coefficient of resistance of that wire, and then the resistance of the wire at 0 degrees Celsius, which is R0. We know that from the relationship, from this equation, R theta is equal to R0 into 1 plus alpha, which is the temperature coefficient of resistance, times the temperature. Now, for the first case, when the temperature is 20 degrees Celsius, the resistance is 30. So we can generate that equation. 30 will be equal to R0, which we don't know, into 1 plus alpha, which we don't know. The temperature the temperature is 20. We call this one equation 1. And at 60 degrees Celsius, the resistance is 34.5 ohms. Resistance at 0 degrees Celsius we don't know, plus into 1 plus alpha times 60 degrees times 60. We call this equation 2. Now, by dividing equation 1 by equation 2, we come up with 30 divided by 34.5 being equal to R0 into 1 plus alpha 20 over R0 into 1 plus 60 alpha. R0 goes with that R0, and then we can cross multiply. When you cross multiply, you have 30 into 1 plus 60 alpha will be equal to 34.5 into 1 plus 20 alpha. Let's expand. This becomes 1 plus 60 alpha being equal to 34.5 divided by 30 into 1 plus 20 alpha. This becomes 1 plus 60 alpha being equal to 34.5 divided by 30 plus 34.5 times 20 divided by 30 alpha. When we collect like terms, we shall have 60 alpha minus 34.5 times 20 divided by 30 alpha being equal to 34.5 divided by 30 minus 1. The right hand side here becomes 60 alpha minus 23 alpha. Then the left hand side becomes 0.15. The right hand side becomes 60 minus 23, which becomes 37 alpha being equal to 0.15. 0.15. Divide through by 37. Divide through by 37. This becomes 0.15 divided by 37, and this yields 4.05 exponent negative 3, and the units are per degree Celsius. For part 2, we are required to calculate R0 from one of the equations. Let's say from equation 1, 30 is equal to R0 into 1 plus 20 alpha. Alpha is the temperature coefficient of resistance. We already have it. Then we do the substitution. 30 into R0 plus 20 times 4.05 exponent negative 3. Therefore, R0 is 30 divided by 1 plus 20 times 4.05 exponent negative 3. This becomes 27.75 ohms. Now you can see that at 0 degrees Celsius the resistance is 27.75 ohms, and at 20 degrees Celsius the resistance is 30 ohms, and at 60 degrees Celsius the resistance is 34.5 ohms. This one justifies why we are saying that this wire here has a positive temperature coefficient of resistance. Why? Simply because the fractional change in resistance per degree rise in temperature is positive. In this example, we have an electro heater which consists of 5.0 meters of nichrome wire of diameter 0.58 millimeters. So they have given us the diameter of the wire, which is 0.58 millimeters, and when you do the conversion here to meters, this becomes 0.58 exponent negative 3 meters. They have told us that the length of the wire is 0.05 meters. When connected to a 240 volt supply, the heater dissipates a power of 2.5 kilowatts. Convert that to watts, this becomes 2,500 watts, and the temperature of the heater is found to be 1000. (1020 degrees Celsius). If the resistivity of nichrome wire at 0 degrees Celsius, at 10 degrees Celsius is 1.0 exponent negative 6 ohm meter, calculate the resistance of the wire at 10 degrees Celsius and then the mean temperature coefficient of the wire at 10 degrees Celsius and 1020 degrees Celsius. For Roman number 1, they just want us to calculate the resistance, and we can calculate the resistance from this relationship. Resistance is equal to resistivity, the length of the wire, divided by the area. The resistivity of the wire is given as 1.0 exponent -6. They have also told us the length is 5. The area can be calculated from pi d squared, but the diameter is given as 0.58 exponent -3 squared divided by 4. That will give us the resistance in ohms. Why am I doing this? Is that we know that area is equal to pi d squared divided by 4. The diameter was given. So you can try out Roman number 2, and this is the answer. So you can see whether you arrive at this answer. Thank you very much.